want to expand on the ideas in our fundamental homomorphism theorem. So let's consider when we have a normal subgroup. Then I get a factor group. Okay. I want to think about this similar to the way we created the sets of integers that we worked in mod 5, or mod any number for that matter. But let's consider what our group behavior became. We started in the integers. Then we had the normal subgroup that was the multiples of 5. And when we wrote this out, we literally wrote 5 distinct sets, right? And if you think of the integers as a number line, what we can think of is we chop this number line into pieces. First piece at 0, 1, 2, 3, 4. The next piece had 5, 6, 7, 8, 9, and we could stack those pieces in line. And we could keep going, both in the positive direction and in the negative direction. Infinitely. And this is our group, the integers. But what I've done is I've aligned it via cosets. Cosets of what? Cosets of my normal subgroup. My normal subgroup is the multiples of 5. That's that first column. And all 4 of these other sets are the remaining cosets. So what I've got is the factor group here on the bottom. Just like in the homomorphism picture itself over here, P mod n is down here on the bottom. So this collection, this is my factor group. And the map that goes from top to bottom here is the map gamma. In our fundamental homomorphism theorem. It takes each element in the integers to the appropriate coset. I like this image. I like this image a lot. I'm going to generalize it. And I'm going to say in any group, I've got a collection of elements up here, right? So I've got things that live in this group. One of those things might be the element A. One of those things might be the element B. Somewhere in here's the identity. All sorts of elements live in here, right? G is a group that's closed. So somewhere in here is the product AB. Now, I can rearrange and align the elements of G by what coset they're in vertical stripes, just like I did here. So let's suppose that here we have a normal subgroup. Why did I draw that through E? But why does the identity have to be there? There in particular. You're right, that's the identity, but why does it have to be in that particular stripe?
So you can do like the left coset and the right coset, and it's equal to each other.
That's why I know it's normal, but not why I know that the identity is in that subgroup. Said the magic word now twice. Say it again.
Subgroup.
Subgroup. Isn't a subgroup a group? Doesn't the group contain the identity? Whatever subgroup I'm in, the identity has to be part of that. And then over here somewhere, I've got the coset AN. And over here, I've got the coset BN. And over here, I've got the coset CN. That last coset, all the way on the right. The one that goes through the dot for AB. I know for a fact that that is not only the coset ABN, it's also the product using coset multiplication of AN and BN. So now I can think of G mod N as having a single element for each of these items. Now up there in the integers, we called those the representatives of our conjugacy classes. And when we did the modular arithmetic back in discrete, we used 0, 1, 2, 3, 4. When I said, what are the elements of Z8 on the exam, Z9, you wrote them down without hesitating, 0 through 8. We could pick any representative of that coset to be the representative of my conjugacy class. And now, this plays the role of the identity in the conjugacy class group. And my other cosets now have this operation on them. So in a way, I want to think of a collapse, a projection from G to the factor group. I take this entire string, we actually call it the fiber over A, and collapse it onto a single element that is the representative of that. So the coset becomes a fiber. And that is ever so slightly different than what we see over there on the right as the image of G. Those were the numbers 0 through 4. Those were the remainders after we divided by 4. Right? And then we defined the new operation, add and take the remainder, by doing an operation down here. And the map between this set and Z4, that's the map mu, that's an isomorphism. And so that's just a relabeling of cosets. So when I say Z5, what I'm really thinking about is cosets of 5Z. I'm just labeling them as the numbers 0 through 4. Page 121 in the textbook, they've drawn this same picture. This visual, I apologize, Reese. This visual shows the lifting that is the coset to the fiber itself, right? So when I say 2 in Z5, I don't just think of the number 2. I think of every number that differs by 5 from 2. All of these. An element in Z5 really coset. In here, an element in the factor group is a coset, a collection of things in G. But what collection then depends on our normal subgroup, on the first fiber in that picture, the one that contains the identity element. And so, I need to look at some examples, figure out what the hell is going on here. Here are two, quote, easy examples, kind of dumb, in my opinion, but they work. The first one, let's make a subgroup. What is the smallest possible subgroup we can have in any group? Just the identity. Closed. 0 plus 0 is 0. 1 times 1 is 1. E is E. Contains the identity. It's got inverses. It's associative. I don't care how many parentheses you put around E times E times E times, you get E. Okay. So that is clearly a subgroup of every group. Is it a normal subgroup? How do I know?
Because E times anything on either side is still going to be whatever element you multiply by. I.e. it's a billion.
Well, not quite a billion, because I don't know if G is billion. For G to be a billion, that would have to apply to any two elements.
Oh, okay.
But EG is equal to GE. Matter of fact, they're both equal to just plain G. And every coset must have the same size as the normal subgroup. So every coset contains one and only one thing. So it absolutely is a normal subgroup. But every coset contains one and only one thing. So my fiber is a single dot, isn't it? G mod n. I'm using this map gamma. But that's not just a homomorphism in this case. That's an isomorphism in this case. Because the kernel, the things that are mapped to the identity, contains only one thing. If I am dealing with the integers, I want you to take the part of the integer that's left over after you divide by 1. Wait a minute. There isn't anything left over, right? Each integer is its own separate thing. If you add 0 to any integer, you get the same friggin' thing back, don't you? So while that is a true computation, and I figured out what my factor group looks like, I just relabeled everything as its own coset. It doesn't help me very much, does it? But this was extreme because it was the smallest possible subgroup I could create. What if I go to the other extreme? I'm in the integers. And this time, I'm absolutely sure it's abelian. The integers are abelian under addition. Means every subgroup is normal. So I know 1 is a normal subgroup. Fabulous. What's Z mod a subgroup generated by 1?
Z
Is what Z?
is it isomorphic? Is the group generated by it the same as Z?
Because Z is cyclic, and 1 is a generator for it. I want you to take what's left over after you divide an integer by 1. 17 divided by 1 has a remainder of. 237 divided by 1 has a remainder of. Negative 32 divided by 1. Remainder is, damn it. How many cosets do I get? everything has a remainder of 0. When I divide by 1, the integers. And that's a group. It's the group we were using up there that only contains the identity. I collapsed everything. So this is the other extreme. Instead of every single coset having 1 unit, I took the entire number line and made it 1 fiber. By the way, that doesn't just hold true in the integers. I could do this in the real numbers as well. Pick any non-zero real number, then NR is isomorphic to R, which means the subgroup generated by N is the real line. In other words, not only are the real numbers generated by any real number, they're infinitely generatable, uncountably infinitely generatable. Bleh, that's disgusting. But that also means that R mod the subgroup generated by N is trivial. There's only one coset. These are the two extremes. If you're dividing by the trivial subgroup, then you really don't do anything. You get an isomorphic copy of the original group. If you're dividing by the biggest possible subgroup, which is the entire group in the first place, then your result is dividing by everything gives you 1. You get 1 and only 1 element. So when my normal subgroup is in between, that's when I have something interesting happen. For some definition of that word. But what sort of interesting things happen? Well, that depends on N. So let's consider something in the middle in a group that isn't abelian. The group of permutations on N things has a normal subgroup. Twice I've done that. Now, we did this last week. How many cosets are there? unfortunately. There are far fewer than n.
Is it one?
There's only one other coset. What's an? Sn is the set of all possible permutations on n things. What's an?
Is that the even?
It's the even ones. So what's left?
Just the odds.
And that's the only other subgroup. Sorry, that's the only other coset. And this is normal, so this is a group. How many groups of order 2 are there? There's only one. So I think of the group Z2, which I can certainly write down. Under addition mod 2, I get this. And if I write Bn is the odd permutations. I just made that up just now. It's not standard or anything, but if An is the even ones, might as well use Bn for the odd ones. When you multiply an even thing by an even thing, you get an even thing. Lowercase, damn it. Multiplying permutations adds the lengths of the permutations. So you add an even length to an odd length, what do you get?
Odd length.
Which would be in Bn, right? Take an odd length and add it to an even length, you get an odd length. Take an odd length and add it to an odd length, you get an even length. It's the same damn table. It's the exact same group. There's only one group of order 2. There's only one group of order 3. Z3. There's only one group of order 5. There's only one group of order 5. Because every prime group order is cyclic. So if the group has order 5, it's got to be the cyclic group Z5. But Z4 versus the Klein 4, there are 2 groups of order 4. When it comes to groups of order 8, oh, we have 3 different options there, right? I have Z8 itself, I have Z2, 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 and I have Z4, Z2, or maybe Z2, Z4, depending on which order you want to put it. We could do the invariant normal form decomposition that we talked about in section 10, where the numbers have to divide, so it should be Z2 then Z4, Z2 then Z4, so the 2 divides 4. So, yeah, it has to do with being a prime. Or decomposable in some fashion. Huh. So what if I had a group of size 24, or a group of size 12, or some other group, right? Wait a minute. You're going to wait. What do you know about the order of every element in this group? I need you to fill in the blank that's the rest of that sentence. Hint. There is a person's name associated to this result. Yes, it has something to do with Lagrange. So now you know what to look for in the book and in your notes. Until I knew he was French, I thought it was the Lagrange theorem. I wonder what ZZ Top had to do with this. But
Divide 12.
aha! The order of the elements has to divide the order of the group, which in this case is 12. So, what things divide 12? Promise that's not a vacuous question.
1, 2, 3, 4, 12.
You missed some?
6.
6. So here's a question for you. Lagrange's theorem says the subgroup generated must divide 12. That doesn't require me to have a subgroup of order 1, 2, 3, 4, 6, or 12. Could, it might not. The converse of Lagrange's theorem says if n divides the order of my group, then there exists H in G with order of H equal to n. This is bullshit. But wouldn't it be so beautiful? Come on, man. If I have a subgroup, its order has to divide the group. So if I know what things divide the group, I know what sort of subgroups I'm going to get. Question. How many things live in A4? How do you get that?
It's the even permutations of 4, so like.
It's the even permutations of 4 things, right? First question, how many permutations are there of 4 things? I give you numbers from 1 to 4. How many different ways can you write down a rearrangement of those numbers? 4 factorial. It's a factorial process. And 4 factorial happens to be 24. Now, Reese, it's the even ones. How many are there? Aha. I didn't pull 12 out of thin air at the beginning. I picked 12 because it's going to be the small example I can make work. Here's the deal. I claim A4 does not have any subgroup size 6. Period. Now that's a hell of a claim to make, isn't it? A4's got 12 different things. I need to look at lots of different subsets of size 6 of A4. That's 12 choose 6. That's not a small number. So I think trying to do this directly by process of elimination, which we could do, would be nauseating. So I'm not going to do it. Which means I need to do this as a proof by contradiction, an existential proof that no such H exists. Kind of hard to do, so we'll suppose one does and see where we can go. Oh, wait a minute. If H is a subgroup of A4 of size 6, then H must be normal in A4. As you live, why should that be true? If I only have one subgroup of size 6, how do I know it has to be normal? Go back up about 14 lines, you'll find exactly the reason. I have a group of order 12. I have a subgroup of order 6. How many cosets does it have? It and one other set, right? Means it's got to look like this. So there are only 2 cosets I don't know what sigma is, but sigma could be any transposition that's whatever's in H and the other stuff, the other 6. Because they have to be the same size. Okay, wait a minute. That means that this table has to look like this table. How would you fill in that table?
Sigma H.
Across the top?
Yep.
Okay.
Sigma H H.
Hey, wait a second. That means no matter what element you pick in A4, when you square it, you end up in H. If you picked an element that was in H to begin with, that element times itself would be H, something in H times something in H. If you picked an element that wasn't in H to begin with, it has to be in sigma H. And something in sigma H times something in sigma H is in H. Oh. H sucks stuff in. Okay. Okay, wait a minute. Let's start squaring things that are in A4. That's an even permutation. 1, 2, 3. It's got length 3 in the cycle, but it's made up of 2 transpositions, so it's even. Great. What's 1, 2, 3 squared? You know how to multiply transpositions from right to left. Tell me what you get. Three, 1, 2 is the same as what I started with. If I write 3, 1, 2, then 3 goes to 1, 1 goes to 2, 2 goes to 3. Isn't that the same as this? It is. Because here, 1 goes to 2, and then 2 goes to 3, so 1 goes to 3. 3 goes to 1, 1 goes to 2, so 3 must go to 2. 2 goes to 3, 3 goes to 1, so 2 must go back around to 1. This is an element of H. I squared something. I found it's an element of H. Hey, wait a minute. 1, 3, 2 is also even. It's in H. What's its square? One, two, three. So that's in H. Hey, wait a minute. 1, 3, 2 is an H. 1, 2, 3 is an H. And notice that the actual symbols I used aren't all that important. What if instead of doing 1, 2, and 3, I did 1, 2, and 4? Which again is 2 transpositions. 1, 4, 1, 2. That's even. What do I get when I square that? Exactly. So this is in H. And if I take 142 and I square it, I get 124. By the way, when you're squaring, I think it's easier to move by twos. We're trying to square 124, right? So instead of just going to the next number, go twice. 1 goes to 4. 4 goes to 2. 2 goes to 1.
If you had a bigger set and it was, say, cube, would you be able to jump by 3? And then that continued on for like.
Given any permutation, raising it to the power means jumping that many spaces. I'm a sneaky mother. Wait a minute. I have two more things that are in H. Thing 3, thing 4. What happens if I do 134 squared and 143 squared?
Get those respectively.
Exactly. Thing 5, thing 6, no matter what else I square, I should get something from this group of 6, right? I started with the premise that I would have a group of 6 things. And I showed that if I had 6 things, then all the squares had to be in there, and then I found 7 different squares. And does it matter what thing I start with? Every even permutation squared must be in here. And there's nothing else between 6 and 12 that divides 12. I must actually be able to get all the even permutations like this. But I knew I was in trouble from the very start of this. What even permutation did I leave off the very beginning of my statement? I left off a permutation of length 0, the identity. So as soon as I found 6, I knew I was in trouble because none of those were the identity. And every subgroup has to contain the identity. Well, so there are actually 8 things. If there are 8, there must be 9, 10, 11, and 12. We cannot make a subgroup of size 6 in A4. No matter what subgroup of size 6 you try and build, it must contain squares, and there are more than 6 squares. But I can only do that because I understand that squares must be in here. And the only reason I know the squares must be in here is because I was able to count cosets. It's the fact of looking at the factor group that allowed me to prove that Lagrange's theorem was not an if and only if. Would have been so nice then. If it worked both ways, oh, look, this is a group of order 24. All the things that divide 24, I must be able to find them. So, the more general question to be asked. How do I figure out what factor group I actually get? We did one of these last week. Z4 times Z2, I think we did. What was the example I wrote up last week? I think it had something to do with Z4 times Z2. I drew a picture.
Mod the set with just 0 times Z2.
And this is the same as Z4 by Z2 mod the subgroup generated by 0, 1. Because what's the 0, 1 plus the 0, 1 in this group? Yeah, what's 0, 1 plus 0, 1?
0, 0.
Which is the identity, which means I've gotten all the way. So the subgroup generated by this contains two things, and it's these two. It's 0, 0 and 0, 1. And then we drew a picture. And I said, oh, I'll put Z4 on this axis. And I'll put Z2 on this axis, and I'll write out all 8 of the ordered pairs that live in Z4 times Z2. And then we created the fibers. We built the normal subgroup. Hey, wait a minute, that's this. That's the fiber that we were looking at back at the very beginning of class. That's this. And so the cosets are parallel to that, moved over by different elements. That's 1, 0 plus my coset, because 1, 0 plus 0, 0 is 1, 0, and 1, 0 plus 0, 1 is 1, 1. What's this one? that fiber. Exactly. And the last one here, exactly. And then I say that those behave exactly like these four dots do down here, like these four elements (0, 0, 1, 0, 2, 0, and 3, 0). Well, if I'm trying to do arithmetic in this group, Z4 by Z2, and all the Z2 parts are always 0, do they count? They really do anything? I'm always going to get comma 0, no matter what arithmetic I do with these four underlined things, right? Which means really all I have to pay attention to is the first number. Which means this group is isomorphic to Z4. I collapsed my fibers into individual elements. And what's more, those individual elements are along the Z4 axis here. They're behaving just like Z4. Oh. What's special about this was that I used the identity here. And my group was originally product. Those factors are the same. So let's suppose I have a product of two groups, H and K. Let's name H bar to be the set H comma E, where E is the identity in K, and H is any element in H we want. Similarly, K bar is the identity in H comma K, where K is any element we want from that group. Then H bar and K bar are normal subgroups. And what's more, G mod H bar is isomorphic to K. And G mod K bar is isomorphic to H. How do I know that? What's the proof of this? Well, the proof of this, that picture right there. Fundamental homomorphism theorem. Why? Because H bar is the kernel of the projection where pi 1 of AB is equal to A. K bar is the kernel of the second coordinate projection. Which means H bar is that normal subgroup, and when I go from the normal subgroups to the image, mu is an isomorphism. That's why I can say that this is an isomorphism right here. Because the fundamental homomorphism theorem says that this isomorphism comes from mu. Hello. So I am using the identity as one of the pieces in my division, my n, my normal subgroup. And I'm going to collapse that whole factor away. That actually makes sense, right? Because when we divided by e, we got the whole group into one coset. So I get this whole part into one coset. And everything else is separated by their element. But wait, there's more. This is another one-line proof. Well, maybe 2 sentences. I want to show that the collection of cosets is cyclic. What's it mean to be cyclic? There's a generator. Well, that means there's a generator for G, right? Now my goal is to find a generator here. I need a coset to generate with. Any sneaking suspicions what coset I could use?
Like multiples of that.
But powers of A generate all of my group, don't they? Which means I will end up with every possible coset because the thing out here eventually covers all possible values of G. And that means I've generated all the cosets. Ta-da. If I've got a generator, let's use the generator's coset. Poof, I get all the cosets. So let's suppose that I wanted to look at what was going on here. This is not necessarily cyclic, because Z4 times Z6, why do I know that's not necessarily cyclic?
24 elements in it, and that's not prime.
But if there were 6 elements, it would be cyclic. And 6 isn't prime. If there were 15 elements, it would be cyclic, but 15 isn't prime. Another word in there that I need. Not just prime. 3 and 5 are relatively prime. 2 and 3 are relatively prime. 4 and 6 aren't. So that's not necessarily cyclic. So what does this look like? What does the factor group turn into? Again, I am visually driven. So I want to know, where are the fibers? What things do I end up with? First question. How big is Z4 times Z6? That should absolutely not stump the room. Yes. What is the subgroup generated by 0, 2?
Usually around the first century, and then all the multiples of 2 up until. Well, you guys want 2 of them.
Say again.
Wouldn't it be like 0, 0, and then 0, 2, 0, 4?
Stop. This second coordinate is only in Z6.
Yeah, 0, 0, 0, 2, 0.
Because then I wrap around, I get 6, and I'm done. I can't go any further. I don't have to go all the way to 24. I only have to go to the second coordinate. So that's a group of size 3. Which means this group has size, order, 8. I should get 8 cosets. But Z8 can be written in different ways. We were just talking about that. It could be Z8, it could be Z2, Z4, it could be Z2, Z2, Z2. I don't know which it is. So my gut reaction is to say, I don't know what this looks like. I'm going to draw a picture. So let's draw the picture. I need 24 dots. To do Z4 by Z6, how do I draw those dots?
X-axis go up to 3. Y-axis you should go to 5.
And then I need all 24 lattice points that would be in my group. Where's my subgroup generated by 0, 2? Oh, that's 0, 0, 0, 2, and 0, 4. I'm going to connect those. Just like we did before, I need things that are parallel to this. Just go across. But if I go across, I get that. I get that. I get that. That's only 4 cosets, including the original one. Where are the others? Shift up. So here, aha! Wait a minute. So up and down does still matter, doesn't it? I didn't collapse everything in the vertical flat. How many choices do I have going up and down for cosets? Just 2. 0, 2, 4, or 1, 3, 5. Odd or even. But going across from left to right, I have 4 choices, don't I? Which means this still has a Z4 left to right. But going up and down, it's only 2. Odd, even. I collapsed, but I didn't collapse all the way because my subgroup was of order 3, and that second side was of order 6. So I cut it in half. There's more. I'm not done with this. This example and others. Pick it up on Thursday. I will see you all then. If you came in late, I still have your homework. Come get it.